Okay, back in Calculus 1, you had functions defined explicitly, it's y equal f of x, and you had them defined implicitly, f of xy equal to 0. When they were defined implicitly, we assumed that y was still a function of x, it just wasn't easy to solve for the y. So when we took derivatives implicitly, we were taking the derivative of any function that was defined in that equation, f of xy equal to 0. Now, as an example, let's say we had the equation x squared plus y squared equal to 4. Now, that's not a function. In fact, if you graph it, it's a circle. We have one function would be the top half, the other function would be the bottom half. So there's actually two explicit functions defined by this equation. Now we could take each of those two equations, the top half and the bottom half of the circle, and take the derivatives of those, separately, but we could also take the derivative of this expression implicitly and get a derivative that applies to both of those two functions. So the advantage of implicit differentiation is if there's multiple functions represented by the equation, you can take that derivative one time and it applies for any function defined by that implicit equation. So we want to look at this now as a surface, z equal f of xy, and I want to take the partial derivative. So I have the function f of xy, which is our z, and we know that's a function of both x and y. Now we're assuming in this that the y is a function of x, and x is just the independent variable. Now drawing our tree diagram to get our chain rule for this particular situation, we have the partial of f with respect to x and the partial of f with respect to y. We have dx. There's one independent variable, so we use regular derivatives, but that's just one. And we have the derivative of y with respect to x. So our chain rule, the partial of f with respect to x times the partial of, or the derivative of x with respect to x plus the partial of f with respect to y times dy dx. Now, I'm starting with this equation, and now I'm differentiating both sides. This is the derivative of the left side, and now the derivative of the right side would just be 0. So I'm using this tree diagram and the derivative of that implicit function to solve this now for dy dx. So take this to the other side. You have a negative, the partial of f with respect to x, over the partial of f with respect to y. Now we can write that in another notation as negative the partial of f with respect to x using the subscripted notation over the partial of f with respect to y. So if we want to find this derivative dy dx when a function is given implicitly, we can do so using just partial derivatives. Dy dx will be the partial of the function f, whatever's that left side of the equation, with respect to x, over the partial of that function f with respect to y, and then negative. So let's see if we can apply that. I want to find dy dx. So that's the change in y with respect to x. And we're viewing this now as a surface with two independent variables. So dy dx is negative the derivative of f with respect to x. So just take the derivative of this expression with respect to x. So it's going to be negative cosine of xy times the derivative of xy. Y is a constant, so it'll just be times y. The derivative of pi y squared is 0. and then minus 1. So that entire thing is the partial of the f with respect to x. Now the partial of f with respect to y. We'll have cosine of xy times x, since our x is a constant in this case. And now the derivative of pi y squared will be 2 pi times y, and the derivative of the minus x is just 0. So this is the dy dx. So it's much simpler doing this as a partial derivative problem than if we actually did this implicitly. Let's review how you actually took this, the derivative of this implicitly. You would take the derivative term by term. Derivative of sine of xy would be cosine of xy times the derivative of xy, which would require the product rule, x times the derivative of y plus y times the derivative of x, which is just 1 since we're taking the derivative with respect to x, plus 2 pi y to the first times the derivative of the y, which is dy dx, minus the derivative of x, which is 1, equal to 0. Now we'd have to distribute this, the cosine of xy through those parentheses. So we'd have x cosine of xy dy dx plus y cosine of xy take dy dx out of each of these two terms and move the other things to the other side. And then the last thing is to divide by that. So we'll dy dx and you'll see that it is the same answer. We just have the minus 1 distributed in the second answer. It's much faster though just doing it as partial derivatives. So anytime you want to just find dy dx and you have a function given in implicit form, you can do it by doing partial derivatives. Just be sure you write the equation first as a function of x and y equal to some constant. It doesn't have to be 0 because when you take the derivative it'll be 0 anyway. But it's just another way to find the derivative